I'm not sure if anyone is there, but I will try to code the upsample bcubic to the MPS shader, and we'll see how it goes. Let me move my terminal to the window. Here we go. So let's try to outline the problem. So there is an issue about missing op coverage, and one of the most frequently requested operator is upsample bcubic 2D. Well, there are many others, but people keep mentioning this here, and here again, and here again. So, and if we look through more of the comment, we'll see this mentioned times and times again. By the way, I don't know if I'm supposed to hear anyone if they join. I'm somewhat new to this process, so leave a comment or something. Anyway, so let's try to understand what is going wrong here by writing a simple unit test. So upsample bcubic 2D is something called an ATON operator. ATON operators is not something we expose necessarily, but people usually access ATON operators through, say, an N layer or an N functional layer. So let's search for PyTorch upsample. Here we go. We say that there is a upsample, which is an N module, but we can also use its functional variant. So let's give it a try. Python import torch. Oh, I need to rebuild torch first. So for the reference, I'm in the PyTorch build folder. So let's reveal it. I kind of tried to prepare for this broadcast, so I stashed changes that introduce a dummy operator, but I did the changes now. So git diff, git branch, well, git checkout main, git checkout dash b malfit mps at bcube sample 2D. Give it a little bit of time to compile, but in the meantime, let's try to look through the documentation and let's try to find upsample. And we say that this has been deprecated in favor of torsion and functional interpolate because people don't want to know whether they upsampling or downsampling. So torsion and functional interpolate. So let's try to write a simple unit test on CPU first while it compiles. So if we import torch and say we have a two-dimensional tensor of one batch, one channel, and 3 by 3, and we want to initialize it with some numbers so we can see how upsample works. Let's call a range. So torch range, and let's specify that we want to have this number of elements, but well, I can multiply it by 1. And then reshape and chw. And my x is not surprisingly a tensor of just 3 by 3. And if I call torsion and functional interpolate x, what is that size scale factor? So let's say one scale factor of 3, and I don't know how to type. And we see that it indeed interpolates, and as the documentation says, it's using the nearest method. Right, so if we use linear, Is it method? Yeah, mode. So if we say mode equals linear, then it will bilinear. So bilinear indeed like interpolates using bilinear interpolation, and if we say bicubic, then it interpolates it this way. Did it finish compiling? No, not yet. Okay. But in the meantime, let's look at the implementation. So 8N operators are usually implemented in like native folder. So I'm in PyTorch build folder. If I go to 8N SRC 8N native, let's say CUDA, upsample bicubic 2D. And I know ahead of time that I will need upsample that will contain some of the helper functions, right? So the upsample bicubic 2D, upframe, there's up elements, height width, accessor, and that's more or less the implementation of the kernel. On the GPU side and down there, we should be able to see the implementation of the operator, which doesn't look like much, but this tells us that upsample is something called structured operator. So we don't need to do all the checks and whatever. We can assume that the inputs has been sanitized when we get the call to this function. Right, and the sample CUDA template, it still checks that all inputs are on the same GPU. Out has been resized for us. We compute number of elements, we compute number of threads, and we schedule a one-dimensional kernel. Well, here we go. It's still compiling, but we're almost there. Okay, so import torch. X equals, sorry. But it's time, let's move it to the device MPS. And if we call interpolate with default mode, it will see the same results as in CPU. Mode equals bilinear. We will see again the same results as we've seen on CPU previously. Please note that the prints are a little bit different, but the values are exactly the same. So like 1.4 to the e minus 8, it could be interpreted as 0 depending on your rounding number. And finally, if we try to do bicubic, I expect we should see the error that people are complaining about, that bicubic 2D is not implemented on MPS backend. Great. So how we can start implementing it? First, we need to create like an operator step. So if we go 8N SRC 8N native functions.yaml, right, and we see we have a CPU implementation, a CUDA implementation, but no MPS implementation. So let's say that we do have one. We go with 2D out MPS. Right, and we can start compiling. And in the meantime, while it compiles, I can turn this one into a single line command. So import torch, right, and chw equals 1333. X equals this guy. And finally, let's print the result of the bilinear. I expect it will just work, and if I do bicubic, it will fail. Right, and now let's wait for the compilation. The compilation should fail because we don't have much here. I wonder if there is any We can only communicate with you through the chat. No, thank you for sharing. I'm not sure how to enable. I can quickly search how to enable voice in YouTube stream. It's how to play some music. Well, compiling. So I've seen your message. I'm trying to log in, and I don't know if I can enable complete sign-in now. I don't know if YouTube allows a video communication. Oh, sorry, like audio chat. Is there audio chat on Discord? I can turn on the mic. And people should be able to talk to me on a Discord, but I don't know. I'm not a Discord user, to be frank. So I know that the compilation will fail in a while with a missing symbol, because we define the operator in native functions.yaml, but we failed to implement it, right? And it says, undefined symbol for architecture ARM64. So obviously I'm compiling it on Mac, on Apple Silicon, so ARM64 it is. So then let's go here, right, and where we were looking at upsample bcubic, upsample bilinear, and I can also look at the upsample mm, right? Let's split and oh, I opened it here. Okay. So let's just grab this guy. Well, so we have a slightly different formatting here. So upsample bilinear 2D, upsample bcubic and bilinear have exactly the same arguments. So if I do something like that, I can very easily have an implementation of upsample bcubic. Right, wouldn't do a thing. And now I also need to include the header. And I suspect if I try to compile again, unless I made a typo, it should compile and link. And I did make a typo. I declared sample bcubic out to D. Did you mean native? Yes. Okay, cool. So now I assume if I run the same example that I run here, let me just copy it, and I have 3 windows, and I run it here. So again, I have a dummy implementation. Metal has a strange feature that it will initialize everything to zeros. So if I run it now, I will not see the error. I will see an empty tensor of the size that's supposed to be the output of my cubic operator. So here we go. Oh, sorry, what? No, that's not intentional. Let me try to adjust the size of the window. Sorry. Okay, can I edit the video capture? And for some reason it only wants to share 1/3 of the capture. Can I? Nope. Okay, I can just try to make my screen smaller. Would that be better? And I can move it towards the left side. You can see it all now, right? Okay, cool. So we have a dummy function. Let's try to implement something that at least copies the value. So something like linear. So to do that, we need to start actually writing the metal shader. Oops, let me close this one and run the split again. So this is how. This is our cubic implementation. So to implement a metal shader, we actually need to write it. There's multiple ways of writing shaders, but one that is currently in use on PyTorch for a while is just embedding the source code and compile on fly. So let me open an example, say 8 NSRC, 8 native PS operators. I recently implemented image to column, so let's just use this one. So we need to implement something called metal shader library, which just contains shader source. So let's start doing this here. And yeah, it can be in anonymous namespace, so we can implement it down there, closer to end of anonymous namespace. Right, and let's call it sample metal. And let's not do the D types for now. We will do it later. I probably wouldn't have time during the stream to do the, well, I can. So let's copy this one. I guess for the people familiar with CUDA, let me open, do it a little bit smaller so that people can see it, and make sure that it's still visible. Is it still readable to you guys? Okay, I can make it larger, right? Something like that. And right, so let's talk about difference between metal and CUDA for a little bit. So in CUDA you can write anything in kind of one C file, and GPU functions are differentiated from CPU functions by having this global O underscore underscore device prefixes, right? Because Metal is just a separate compilation unit from the program point of view. You don't need to decorate it with any special symbols, but global is still helpful. So, well, kernel is still an important entryway to say that this is an entry to a function. So let's copy, I don't know, let me see if there's any more comments. No, looks like you guys can. Okay, cool. So let's copy this template dummy. So image to column and upsample bcubic to D is somewhat similar in inputs and outputs. Well, there are some differences, and we're not going to do aligned corners, I think, during the stream. So what you need to pass to the kernel, you need to pass your input tensor, your output tensor, your tensor dimensions, specifically strides, and something called thread index. So if in CUDA the thread index is a magical environment variable that is available to every kernel, right? In Metal, it is passed explicitly and decorated as thread position and grid. So let's try writing our kernel. So I can copy like a chunk of this one. Where is my library? No, I deleted it. Okay. Okay, and we define a kernel here. So let's define a kernel which have a template input type, output type. We have input strides, output strides, and I guess we need output sizes. Do we need input sizes? Probably we need both input sizes and output sizes. No, we don't really need output sizes because for output we already know. Cool, so let's do that. So we have 1, 2, sorry, 2, 3, 4, and thread position and grid. And let's do something as simple as output data of thread index dot x, output strides dot x plus thread dot y multiplied by output strides. And let's just do thread index dot x. right? And we instantiate the template. So the way we need this instantiate image to column type, because you need to, like, the interface between Metal and CPU is a C-like interface, so it needs to know the explicit function name. It couldn't have a template, so we need to specify direct column name, and so we do something like that. So let's call it upsample bcubic. Right, and we call it instantiate upsample bcubic. Input data, so we ignore this. 0, 1, 2, 3, 4. Let me check if I have any comments. Sorry, what is the question about thread index.x multiplied by? So thread index is in get, like, if you think about the either CUDA or Metal kernel execution, you can execute kernel using one-dimensional. Oh, is that a typo? Index thread index y? No. Output strides, or no, everything's correct. Oh, index, got it. Thank you. So here's a funny thing. Maybe we should leave it as is, and we will observe something interesting. So the problem with compiling at the runtime, at the compilation time, we wouldn't notice that we made a mistake, and then I'll talk about this kind of strategy, how you can make it more noticeable, right? But so I will make a typo later on, but thank you for pointing out. Right, so I do that, I defined template instantiation, let's say I instantiate it for float, right? Right, so instantiate upsample bcubic. Right, and let's see if we can still compile. We don't do anything interesting, so we can compile. Because this is an OOP, right? So what this does is says, I create something, almost everything in PyTorch is lazily initialized, so until this function is used, we not try to compile it, so no one will notice any difference. So let's again follow the general implementation pattern, and we say that we have, what is that? Upsample out template. PS upsample out bcubic template. Right, and input output size, align corners, scales, H scales, W and output. Right, upsample out template. So let's find the template up there and just implement something similar for the bcubic template, but try to use the kernel we just implemented. And feel free to ask questions. I know that it might be a bit hard to follow. Let me make sure that I can see window with the chat here somewhere. So if people ask questions, so sample bcubic out template. Right, so let me get to my buffer one because I'm a little bit. So output size, I don't do input size, I do align corners, scale H, scale W, output, and that's about it. Right, and if tensor is empty, we're not doing anything. So now we need to call our kernel. Let's again steal it from image to column, which does a lot of things. But important part is we try to get a function from a library, right? So as soon as we do this, this will force recompilation, right? So we say upsample PSU, get pipeline, upsample bcubic 2D. So now again we will see just outputs, but we will see if I make any typos in the shader. So if I'm going to compile it, hopefully it will compile. Still, I don't know. So I have upsample bcubic, upsample out bcubic versus upsample bcubic out. Okay. Okay, cool. So it compiles. Let's see what will happen. I very much suspect that I probably made a typo somewhere in the kernel implementation, and we will see it pop up here. Yes, I did. So I have another typo. Instead of output strides, I did output strides, and we can see it here. It's kind of painful to compile it every time like that, so let's do a simple thing. Let's create a new foo.metal. Oh, I already have foo.metal. Let me delete this guy and let me make this. B1. Here's my library. I'm going to do just copy everything to here and invoke the compilation. Right, so I have my kernel code here, and I can just look at it here, and I can do xrun metal foo.metal, and I will see the same error. So it's much faster than waiting for this one. So output, and I need T, and hopefully that's the only error. So I can copy it back here and compile again. And hopefully, again, we will see only zeros, but it will compile get me a function. Yep. And let me, anyway, so what we achieved so far, 30 minutes into the stream, we implemented a dummy function, we implemented a dummy metal kernel, and we can compile the kernel. Now let's try to pass some arguments. Okay. Let's get back to my, so now I'm going to do this, dispatch sync with rethrow, and I'm going to create a stream, and I'm going to talk why this is needed. So many GPU APIs, whether it's Metal or CUDA, require one to serialize all the access to the stream. So here we're saying that, whatever Python thread is going to call this function, there shouldn't be any concurrent calls to a Metal or MPS APIs for the given MPS stream. So MPS streams and CUDA streams are very similar technique and similar idea. It allows you concurrent execution, so everything that is submitted to the stream will be executed sequentially on GPU. So every kernel will be executed in parallel, but if you submit kernel A and kernel B, they will be executed one after another. On the other hand, there is no synchronization needed, so I dispatch the job to GPU, and GPU will be executing them as is. So here we go. Right. So we serialize, and here let's try to preserve our output strides. That's the thing I care about. And I can say I take the encoder from my stream, I bind the stream to the pipeline, I pass inputs and outputs, so metal set buffer. Again, we can see that input buffer is argument number 1, output buffer, argument number 0, output buffer is argument number 1. So we're going to pass those, and let's pass output strides, that's the only one we defined so far, as it's buffer number 3. And last but not least, let's dispatch the kernel. Right, what I'm going to do here is I'm saying I'm going to dispatch a 2D, well, here I'm dispatching a 3D kernel, but let me dispatch a 2D kernel with output size. And also output a 3-dimensional, so I can just do it like that. 4-dimensional output stride of 0. And I say output size of 1, output size of 0, sorry, and CHW, so I need 3 and 2. Again, 3 and 2, this is 1, and let's say I wanted to execute it in blocks of 8 by 8. Will it compile? No, which is file being edited on the right now? it says it down there, right? Every time I edit a file, you can see the file name in the Vim at the bottom of the window. And I made some silly typo somewhere. Oh, yes, I don't need a semicolon here. Keep sample 1, 0. This one is strides is 3. I have output size 3, output size 2, 1. And I'm dispatching, and this is closes everything. Am I 267? Okay, so we do this. Oh. Now, for those not familiar, okay, it compiled. Let's see what will happen. I'm curious. I'm somewhat doubtful that I will do everything correct. We crashed, which is a bad sign and good sign. We'll try to debug what's going on. But in the meantime, let's see what we're doing. So for those not familiar with Objective-C, this is something called a block. So the block is very similar to Lambda in C++, but it have a little bit different capture semantic than C++, and it appeared like blocks in Objective-C appeared, I don't know, in early 2000s versus lambdas is part of the C++ 11. Okay, so we do this. We want to output. Let's try to compile this debug information and see what's going on. So first of all, I'm going to attach the debugger, and also I'm going to recompile this one with debug information. Tools build with debinfo 8 and src 8 and native MPS operator subsample mm. Oh, I think it becomes, because it needs to rebuild almost everything in Torch Python. Oh, and I see that window is, I'm not sure what's going on, why it's making screens smaller and smaller. So you only see stream of this portion? Is that correct? Can you see the entire screen now? Is this one better? No. So macOS screen. Scale filtering disable. Oh, no worries. Yeah. I'm trying to figure out myself what's going on. So can you see? No, you can't see the entire screen. It's even smaller now. Give me a second. I'm Trying to see what I did wrong here. Properties, display capture, entire display. Scale filtering. I have so you see the entire window and a little bit of documentation, right? And this would be like entire window is taking the screen, right? I can put my own image somewhere here. It's not important. Cool. So can I compile sample with debug information now? I hope I can. And let's attach the debugger to it and say that I want to set a breakpoint in upsample bcubic output template. Okay, cool. So we can say we see output size as an array, output size of 0, 1, 2, 3. What? Interesting. So we need output size of 0 and 1, not 2 and 3, and this is what's causing the crash. Because so suspect now it will just run. And print 0, 1, 2, 3, 5, 6, 7, 8. So what we see here, it's not that exciting, but it means that kernel is being executed and it runs a very simple command that we're trying to do here. So what we need to do now is to capture input sizes as well. Input strides, input sizes, and well, actually I need output sizes. So let's add output strides, input sizes, output sizes. As buffer 5. Please note that even if I don't pass anything, it works just fine, right? I can only pass the one I care about, but let's pass everything. So output strides, input strides, let's do output sizes. well, let's still compile. Still does. And let's so input strides, output strides. Output strides is 3, input strides is 2. Is 5 will be output sizes. Does this sound correct? Looks like it. And now we actually need to implement the algorithm, right? So once again, let's try to run. It shouldn't change anything as far as I can tell, unless I made a typo somewhere. Yes, it doesn't change anything. So now we try to implement the algorithm and actually do the bicubic scale. Well, let's do nearest first. Well, maybe not. Let's get to the bicubic.cu, right? Oh, and this is where I implemented the library. That was stupid of me. So once they get the output and input, they want to scale output x, align corners, area pixel compute source index. And where the area pixel compute source index function is. I guess it's in this file, upsample ch. Right, so it takes scale, destination index, and whether it's bicubic or not. And we have a scale, and we can always estimate the scale as output size divided by input size, can't we? So our scale W would be sizes of x and divided by input sizes of x. And scale height will be output sizes of y. So let's now we can just copy this function. Into our shader, we just can remove device force and line, and it becomes the same thing. So it's not ing, it's long. Is it? Or is it integer? It's signed integer. So we have scale, destination index, Oh, so scale is inversed. It's input sizes divided by output sizes. But we just want to have like a nearest, right? So let's say we just take and I don't know if there are any questions. Any questions so far? Note? Okay. And I'll again, let's try to compile. And let's see how many typos I've made now in the code. And looks like we have nearest interpolation as a bicubic one, right? So our input is, once again, if we look at what we're trying to interpolate, X is this guy, 0, 1, 2, 3, 4, 5, 6, 7, 8. So linear interpolation work. Let's keep like, I guess what we need to do here is essentially just copy the logic from upsampled bicubic into the shader, and it will automatically work. But again, we're kind of ignoring the line corners now. So let's so this is upsample. Buffer is that I want to be B2 upsampled bicubic. So let's try to see total calls the template. And let's call it with scale. this would be to kind of follow the same pattern. We scale, height scale, and let's say pull align corners equals false, because we don't pass it here. So output X, output Y. We scale output X, align corners bicubic true. And now we have in X and TX real Y, TY, right? And again, let's try to keep the same idea. It'll be in X, in Y. Right, will it compile? I should have made a typo here somewhere. Okay, so we have out Y and output Y. What's the difference between output X and out X? Output X and what is out X? And oh, there's no out X. Oh, there's an alt code, right? Now there is no floor F, there is a floor. So that's the difference between CUDA and Metal, is how they treat built-in functions. CUDA is more C-like, Metal have a more C++-y nature. Oh, and yes, I need to do using namespace Metal at the beginning. Using namespace Metal. Here we go. It's a C, not a Python. Yeah, well, we're doing something weird here. But I guess it's a bit by design, because bicubic behaves like, oh, we're doing floor. So bicubic behaves slightly different than bilinear. So let's keep copying more code, and we'll probably get very close to where we want to be. Right, so we are in upsample bicubic to the out frame. So we have our four coefficients. Any questions? Oh, looks like no one's viewing now. Well, I'll keep trying for a little bit. So now on the CUDA side, we're using the back tensor accessor, which is a class that we don't have implemented in Metal, and I don't want to do it now necessarily. And again, I'm kind of deliberately ignoring width and height. Sorry, batch and channel. Min max. So let's write something like that. So we have input data. Let's say we have int2 dim and u long 2 strides. And what else is there? And long 2 into chord. Right, because all it does, it says x6 so width and height is dim_x, sorry, dim_y minus 1, dim_x minus 1, and yeah, let's call it data. So it says data axis y multiplied by strides. And once again, let me just copy this one because I don't want to I go to my cells buffer. I want to just compile the shader and see what will happen. And yes, indeed, there is no iData. Put data. So xy input strides xy. And here we have let's repeat it here. Sorry. Unknown type name T because it's scalar T. Because I need to put include here. I keep forgetting what this include is. That's the difference between compiler and method with just-in-time compilation and compiling it with like outside. And let's go to B5. No, I'm not including metal heap. Oh, I see some questions. I understand that this you're writing MPS version to closely match CUDA version. Yes, so that's what I'm doing. I want to show that essentially like Metal and CUDA are more or less the same. Yes, so C++ and CUDA and C++ and Metal. Yes, that's exactly the idea. So I want to show that, you know, if we have a missing operator and we have a CUDA implementation, we can take more or less CUDA kernels and just use them. But yeah, now I'm trying to remember what is that metal library include. I have this an example. Oh, metal array. Do I need to include metal library or something? So it doesn't know what floor is, even though I say use a namespace metal. Um, I keep forgetting the name of the includes. Oh, let's look at some other shaders that we have. Native. Metal STT-lib, that's what I was looking for. Now we have something. So min call is ambiguous because we have integers and we have longs. Metal is very specific about data types. So we have, so those should be longs. Max is ambiguous. Used variable ty. Okay, I need cubic interp 1z now. B4. So now I'm going to copy this function. Cubic convolution 2, cubic convolution 1. Okay, cool. So looks like if we do all that, it just works. And now the final piece of the puzzle is right. So we go here, and when we copy the data, we do this. And that's it. Looks like this is our shader. If we copy it, presumably it's just going to give the same results. So P1, let's just delete everything we have here, copy the shader, it is compilable, right? And it needs some cleaning up in the end, but hopefully presumably that will give us the same results as on CPU. And I guess that kind of achieves the goal. It needs a little bit of cleaning, the code is ugly, but that's the gist of it. I will submit a PR later today. Yes, and if we can see, CPU and metal shader outputs are now identical, right? So I run it with bcubic on CPU, and I run it with bcubic on metal. I don't know. I can try to answer some questions if folks have them. If not, I can try to finish the stream. Well, not try to, I will finish the stream and share PR later on. walk through high-level recap. So what we did during this stream is we figured out how to we walked through an example of how one can implement a metal shader for a Meson MPS operator in PyTorch by adding a dispatch function to a native functions.yaml, right? So get diff. Well, let me just create a PR, whatever, however ugly it is, and I'll publish it, and I'll maybe walk over it a little bit. Git diff. So we just modified upsample native function.yaml, MPS, sample cubic 2D as metal op. Right, so git branch, just making sure I'm not a master. And let's create a PR. So at the high level, we added a dispatch to native functions.yaml. We implemented the dummy function. We created something called metal library, which embeds the shader into the source code. I demonstrated how shader can be implemented and how you can test your code. I think the only thing that is kind of missing that is somewhat cool is show you an Apple's Xcode shader debugger, right? So because if you mess up with the algorithm, it's so on the high level, like if for GPUs, for CUDA GPUs, you use mixture of C++ and CUDA. For Apple GPUs, you can use MPS, which is similar to, I don't know, CUDA and cuBLAS library, so it contains a lot of ready-made operators, or you can write your own shaders when something is missing in the MPS side. Bicubic interpolation is one of those things that is not available as part of the Metal Performance Shader library as of macOS Sequoia or whatever, and so one have to implement it as a metal shader. Like interface for interacting with metal shader can be is a bit clunkier than CUDA one. But essentially it looks as follows. You get a library, you get a current stream, you synchronize your execution of the stream, you submit a work request to the metal pipeline, which perfectly interrupts with every MPS graph that you might have. You bound the input arguments. Unfortunately, they just bound by index. And you dispatch the kernel, which so this compute encoder dispatch threads is very similar to like on CUDA I would write something like upsample bicubic 2D kernel, right? And here I would say output size 0, so I dispatch it as a two-dimensional kernel. Output size 1, and right, and my grid size would be a two-dimensional 8x8 kernel. So that's essentially what I'm doing here, right? This whole code is right. So on CUDA, the following 10 lines are identical to this invocation. So let me show you how to, like in Romanian time, show you how to capture the shader state and debug it later in the Xcode. So you can do something like to capture the status of shader, you can use MPS profiler to say if capture is enabled, I want to capture something called upsample bicubic 2D to a stream, And at the end, I say if capturing, then stop capturing. If I compile the code like that, then I need MPS profiler. Let me add this code here. So I'm just including MPS profiler to enable the capture mechanism. When I define compute, what did I do? Oh, compute encoder, I defined it twice. So again, if we run something on MPS, but we add, nothing will change. But if we add something called metal capture enables equals 1 to our command, we should see something upsample GPU trace, which is something that Xcode can open. If I can open the right one. And here we go. And I can ask for replay. And my GPU capture is empty. Let's see what I did do wrong here. I enable the capture and is capture, and I stop the capture after I dispatch the workload. Let me try again. Why would the capture be empty here? But indeed it is. Do I need to do something like that? Probably this one will focus pipeline flush. Let's see. No, it's still 24 kilobytes. Oh, I guess that's because I'm streaming. Sorry. It's a little bit weird. I cannot capture while I'm streaming because it's a GPU shaders, I guess. Well, I cannot show that, but it's a pretty nice feature. So if you decorate the code with these decorators, you can capture the. Do I need to do it before command? No, compute encoder, I do it. Let me try with image to column. Would it be empty as well? no, this one works, so I'm doing something weird over there. But let me demonstrate in a different kernel, which is not the one that I just wrote, but I don't know why it works in one case and fails in another. So this captures the pipeline state that we just created on the metal, and it captures my function, and I can even debug it for a specific thread, right? I say I want, for example, thread 2, and I can run debug, and I can observe the values of my kernel. So it's slightly different kernel, but I see all the values passed into the kernel, and I can see, like, I can select the first iteration, and at every step I can see the value on that line and what I'm writing, what I'm accumulating, and all intermediate variables, and so on and so forth. So this is a pretty convenient mechanism. If you struggle with understanding why your shader does not perform in the way you expect it to perform, you can do something like that. Moreover, you can edit the shader here and attempt to rerun and see how the values will adjust on the fly. So I recommend one to try to use this one. And if you like at a dead end and don't know why your shader produces the wrong results, that's kind of the only shader available for Meta. The only debugger available for Meta, but it's a pretty versatile one. Cool. I don't know if anyone have any other questions. I'm not sure. Yeah, it's not a stream disrupting it, but I'm doing something potentially weird. I need to debug a little bit more to understand why it's not happening, because usually this should be sufficient. So for interpolate, okay, it says that my capture already exists, which is a good sign. When something like that happens, it's usually the sign that something is wrong with MTL Apple Metal variables sanitize. MTL shader validation equals 1. Let's see what will happen if I do something like that. No, capture as a shader during validation is not supported. Makes sense? Let's not capture, let's just do the validation. And no, I don't do anything wrong. So I validated my shader. Sorry, I realized I decided outside of the visible screen, but I still cannot capture anything. I need to debug it further, and I guess I don't know how to do it during this stream. But yeah, like it looks like whatever you try to do, it generates an empty shader. Begin profile, upsample PSO, upsample bcubic 2D, is capture start capture stream, and if then stop capture stream. And the stream is where should I just capture it outside of the dispatch or something? No, I do it within the stream. So I'm somewhat confused why it works in one case but fails in the other. I bound the command encoder, I do dispatch, and after I do dispatch, I stop capture. That should be sufficient. Anyway, I don't know. Any other questions? Would I be willing to give a talk? Yes, sure. I probably need to prepare some slides, but I already talked to Mark about it, that at some point maybe I'll do something along the line of a more structured presentation where hopefully there would be audio chat as well. I can hear your questions rather than reading them 5 minutes later. And yeah, so that's coming. I don't know when. It's up to Mark when he schedules it, and up to my availability as well. Anyway, thank you for your time, and have a good day or whatever evening. Bye.